Welcome to the lecture on materials. This is Materials 1, where we will talk about simple materials that reflect light only in ever exactly one or two directions, that is, mirror materials and dielectrics, and also the effects that they cause on their surroundings. Later on in the course, we intend to also have another lecture for Materials 2, where we talk about advanced models, for instance, the microfacet models and different applications of that. Today, we will look at the following topics, which we need to add a great new feature to our path tracer. That is, we want to account not only for light that is reflected, but also light that goes through a surface, which gives us the ability to get some see-through effects, as you can experience them in the real world for glass, fluids, and similar see-through materials. We will define a bidirectional transmittance distribution function and look at what we can do with them. Following that, we will draw a few conclusions that partly derive from the steps we took to get refractions going. There are some important terms that you should definitely know when you enter the world of rendering. Let's get right to it and see what we need to know in order to make light go through objects. First of all, we should distinguish the possible viewpoints that we can have for how light behaves when it hits a material. We distinguish two ways of deriving the computations that we use according to two different models of reality. The first is the model of physical or wave optics. The interactions of light with materials are described with a complex model of light where we treat it as a wave and basically try to find the solutions to Maxwell's equations. This is definitely the more difficult but also the more detailed approach, as it captures many effects that occur on the supermicroscopic level. For example, to account for surface elements that are smaller than the wavelength of the visible light. Simulating it is computationally expensive, but there are usually diminishing returns in terms of visual quality. So in practice, we will generally use a reduced precision model based on geometric optics only. That means we usually ignore any effects that occur at a scale that is smaller than the wavelength of light. We assume that we have some parameters that tell us the scattering properties of surfaces and use them as input to compute closed form solutions of reflections. This makes computation a lot easier, but also means that we are losing some detailed effects, like those that would, for instance, arise from light polarization. But since these effects rarely make a big difference, and most people wouldn't even know what they look like, we will be ignoring them for now. The full name of the BSDF, as we already mentioned it quite a few times before, is the bidirectional scattering distribution function. And it's the part of the rendering equation highlighted here that so far we mostly ignored or replaced with something constant or easily to compute in examples. And the job of the BSDF is to describe the transport of light by a material. Specifically, the result of the function, as it is written right here, is the amount of incoming radiance from a direction omega that is passed on to a different direction v at a surface point x. In our case, for the rendering function, v will always represent the rate that we followed to get to a hit point x, and omega is the next direction we look at. In the case of direct lighting, which we saw before, V would be the view ray, X the point the view ray hits, and omega would be the direction we follow to find a light source, or not. This term opens up a whole new universe of options because, as we mentioned, its job is to represent the light transport characteristics of materials. And there are as many different behaviors as there are materials out there. Some of them are translucent, some of them are shiny, some of them absorb most of the light they receive, some of them reflect all of it. So this is potentially a big topic. But for now, we will only look at a subset of effects that the BSDF can model. For now, we will only consider materials where light is either absorbed, that is, lost in transport, or reflected at or immediately below the surface. So no particle scattering, translucency, subsurface scattering, or similar for now. For such materials, it suffices to define a relatively simple BRDF, a bidirectional reflectance distribution function. The BRDF as a concept is a subset of the BSDF and is usually what we start out with when introducing the topic of materials. The BRDF has several important properties. It is parameterized by two directions and gives the portion of light that, when coming from one direction, is reflected to the other by the given material. It is a convention to always use directions as inputs that point away from the point at which we evaluate the BRDF. Here we have the formal mathematical definition of the BRDF, and you can verify for yourself that it is the missing piece to plug into the rendering equation to balance the outgoing radiance with the integral of the incoming radiance. The order of the vectors with which the BRDF is parameterized doesn't matter. BRDFs should ensure the Helmholtz reciprocity, that is, if a certain percentage of light coming from omega I is reflected to omega O, the same amount would be reflected from direction omega O to omega I. Finally, for physically plausible renderings, the BRDF must ensure that it does not add energy to the scene. So the sum of reflected light must not surpass the amount of incoming light. A BRDF ensures this if, for any direction v, the integral over the hemisphere of the BRDF times the cosine of theta is smaller than 1. Now this requirement is important, but it might not be too intuitive in its formulation, so let's have another look at it. We just learned that a BRDF supports reciprocity, meaning the portion of light reflected from A to B is also the portion of light reflected from B to A. Thanks to reciprocity, there's two ways that we can read this. We use the BRDF in the rendering function where it is supposed to be used. In the first interpretation, the amount of light that is reflected from X into one direction V from all possible directions omega must accumulate to 1. But perhaps the more intuitive interpretation is that a certain amount of light, for example from a laser that arrives at X from a given direction V, can be scattered. The total percentage of reflected light that observers around X will be able to see, according to the rendering equation, is the integral over the hemisphere of the BRDF times the cosine of theta. If this yields more than 1, it means that the observers see more than 100% of the incoming light, and this violates energy conservation. We generally distinguish three different types of BRDFs. Note that this is not yet entirely physical, but rather a widely accepted convention to categorize materials by their appearance. We also briefly saw this before. Those that more or less evenly scatter incoming light in all possible directions are referred to as diffuse. And a perfectly diffuse BRDF is uniform for all possible pairs of directions. Materials that reflect light only in a very small range of directions, that is, they mostly mirror it, are referred to as specular. A perfect mirror reflects any incoming light only in the mirror direction. And the last group are glossy materials. They have the qualities of both diffuse and specular materials, that is, a certain amount of light is scattered in all directions, but highlights can be seen stronger from directions where incident light is mirrored. Note that for specular and glossy materials, the shape of the BRDF actually depends on the vector v, that is, for our purposes, the direction from which a view ray arrived at its current hit point. Here we have three example renderings that we saw before of the HX bust, just to repeat them here. One with a perfectly diffuse BRDF, one with a perfectly specular BRDF, that is a mirror surface, and one with a glossy BRDF. And we can easily see the differences in their light distribution properties. The diffuse materials almost have a certain basic ambient brightness because most surfaces reflect some light in all directions, but they completely lack highlights. On the other hand, the specular BRDFs only mirror any incoming light and don't show any scattering at all. Lastly, the glossy BRDF shows both of these effects, but to a lesser extent. Remember when we talked about importance sampling before, and we considered that it makes a lot of sense to basically encapsulate BRDF relevant code into its own class, so that we can have easier BRDF sampling, such as the cosine weighted hemisphere sampling for the perfectly diffuse materials. So we already have applied some optimizations based on the knowledge that BRDFs exist and that the sampling behavior is also dependent on them, and implemented it as part of our cosine weighted hemisphere sampling for diffuse materials. Let's quickly revisit how we have implemented the diffuse material before. Consider a material with a diffuse color ρ. Color means that the RGB values of ρ tell us how much of the light in each color channel is reflected. And those values must be less than 1. Due to energy conservation and the definition of ρ, we know that the integral of the BRDF times cosine of theta over the whole hemisphere must equal ρ in each color channel. Either by solving the math once more yourself or by building on the results from previous lectures, we can choose the BRDF to be ρ over pi for any pair of directions in the hemisphere around the normal. Note that this is exactly what we used for the evaluation methods for our diffuse BRDF implementations. So now we see that we actually used a correct mathematically motivated BRDF for diffuse materials. But what we also saw back then was a way to make sampling for the simple uniform BRDF more effective. If the BRDF is uniform, then the only thing that we can predict and that varies in our rendering equation is the cosine of theta. So in order to importance sample the diffuse BRDF times the cosine of theta, all we have to do is cosine weighted hemisphere sampling. Let's now look at a completely new material that we haven't talked about before. That is the specular material, or the perfectly specular mirror material. We can derive a BRDF for a mirror reflection where all incoming light is reflected only in the mirroring direction, which is defined as having the same angle towards the surface normal, but pointing away from it in the opposite reflection direction. We will look at the purely specular or mirror BRDF to add as a feature to our scene and path tracer. For this BRDF, the incoming light is completely reflected in the direction V if it comes from the corresponding mirror direction around the normal. This mirror direction has the same angle towards the surface normal as V, but lies on the opposite side of the hemisphere. We denote such a perfect mirror direction of a vector V as R sub V. Light is only ever reflected by the surface in a single direction for mirror materials. So for any combination of directions that are not mirrored versions of each other, the BRDF is 0. This distribution is simple enough, but it leaves us with a problem. We cannot sample it like we did for the diffuse BRDF. If we have a given V, then we cannot simply use uniform or even cosine weighted hemisphere sampling or something similar, because the chances that we will hit the exact mirror direction of V are infinitely small. If we want to get reasonable results, we actually have to use a special method for sampling the specular BRDF. To do this, we first try to see if this particular behavior can be expressed with a formal mathematical distribution. The solution to this is the Dirac delta function. It is actually a perfect fit for what we are trying to describe. Formally, the Dirac delta function delta of x is defined to be 0 everywhere except at x equals 0. For our purposes, and given a vector v, we can use a shifted version of the delta function delta v of omega, which is 0 everywhere except at omega equals the mirror direction of v. If we can importance sample this distribution, then we should never get a direction that is different from RV, because all other directions would have probability 0. To make it a valid PDF for sampling, we must ensure that the integral over the hemisphere is 1, of course. This is ideal in theory. There's just one question that you might want to ponder for a moment. What actually is the value of delta V at the reflection vector RV? This will come back to us in a minute, but first let's check if we can make a valid BRDF from the delta function. We already have reciprocity because the mirror direction of RV is again V, so we only have to check for energy conservation. We actually want to have a complete mirror BRDF, so no light is absorbed or scattered, meaning that for a vector V, the entire radiance from its mirror direction is passed on. If we integrate the incoming radiance from all directions times the BRDF over the entire hemisphere, we want to get exactly the light from the mirror direction. Let's see if that works with the BRDF candidate that we just found, the delta function. We know that the integral of our delta function, as per its mathematical definition, over the entire hemisphere must be 1. We also know that it will be 0 everywhere except at RV, so the result of the integral must be the light from RV times the cosine of theta at RV. But this means that we lost some light due to the cosine term. And therefore we compensate for this by defining the values of our BRDF as the delta function of V divided by the cosine of theta for the mirror direction. This way, all the light that comes from one direction is passed on in the mirror direction by the BRDF. So since we know the PDF that we want to use, the delta function of V and the actual BRDF values, we can try to implement the same functions as we did for the diffuse BRDF before. The sampling method is easy. If we have a given vector v and a normal n, the only sample that we can ever generate with the delta distribution is the mirror direction of v, rv. But for the other methods, we face a problem. We are supposed to evaluate the BRDF for any two vectors. Remember that what we should return here is the ratio of the radiance that arrives on the surface from one direction and is reflected as radiance to another. This is easy when the two vectors are not mirrored versions of each other. But what if they are? Here the question comes back. What actually is the value of the delta function at the exact mirror direction? The answer is it's something that tends towards infinity. The same is true for the PDF function, which leaves us in an awkward situation. The only reasonable way to go here is to make sure that the evaluate and the PDF functions are used together, because in that case, the delta function cancels out. Luckily, this will also be our main use case for the path tracing routine where we use this material in. With this in mind, we go back to the specular BRDF and take a closer look at its updated version. We will now assume that any operation that actually wants to find the proper mirror direction for an input will do that by using the sample method, which for a given unit vector v always produces rv. We will also assume that no function other than sample can simply guess the perfect reflection direction. This makes things easier in code for us because we can simply ignore the infinity values and just always return 0 for the evaluation of BRDF directions and the PDF alike. And here we can see the immense difference that this makes. Replacing diffuse materials with specular mirror materials immediately add an effect of interesting visual quality to our scene and can make them more complex and more interesting to spectators. With this current implementation done and having the ability to render mirror materials, it's time to revisit it and extend the concept of only ever passing light on in one, or in the new case at most two directions, when we go to an updated material that is dielectrics. With the mirror materials, we assume that all of the light is always reflected, regardless of where it comes from. But there are no materials in the real world that actually do this. Most of them will allow some of the light to either be absorbed, scatter in all directions, or go through the material. That means some of the light is reflected in one direction at the surface. This is specular reflection. Some of it enters the material it hits, but immediately exits again and is scattered all around. That is what we see as diffuse light. Some of it enters the materials, and the atoms in the material happily take the energy and later release it as heat. This is absorption. Yet some of it enters the material and just keeps going because the material acts as a medium for transmission. That is, it is not ready to accept the energy that it is given, so it lets it pass through. If that happens, we usually call the meeting point of these two media an interface, for instance, from air to glass. What usually happens is, due to the different density of two media, the light will be slowed down or sped up and change its direction when it goes from one medium to the other. You've certainly seen this. For instance, if you put a straw in a glass filled with water, it seems to bend at the surface when you look through. The way in which light changes direction when it goes from one medium to another is governed by the material's indices of refraction and Snell's law. Here we have a direct comparison of a mirror material that we previously described and an accurate simulation of a diamond statue according to the indices of refraction that are being used. Clearly, we can see on the right that some of the light is allowed to pass through. We can see through the statue and the shadows are not as dark. But at the same time, some light is also reflected on the surface as highlights. This particular material is a dielectric, meaning that it's fully modeled by specular reflection and refraction. We will shortly see how we can recreate this behavior and make our path tracer do this. But first, Snell's law. As mentioned, Snell's law tells us how a light ray changes direction when it goes from one medium to another based on the involved media's indices of refraction. If we follow a light ray, we use eta I for the index of refraction of the medium that it comes from and eta t for the index of refraction of the medium it goes to. This index gives us a relative measure of how fast the light travels in either. We will not derive it here, but Snell's law essentially gives us a way to equate the directions before and after the interaction with the formula eta I times sine of theta I equals eta t times sine of theta t. Note that the directions on the sphere are defined by theta and phi, but the equation does not include any change in phi, because the ray does not rotate about the normal. Note also that on the right-hand side, we currently see the way that a photon would travel. But as with the BRDF, we will be using a notation where both vectors point away from the point of interaction. With Snell's law, it's not difficult to derive the new direction by solving for theta t and using it to construct a new ray. There are many explanations for Snell's law from different kinds of backgrounds. One would be, for instance, that due to the different speeds that light has in different media, it also must change direction because light will always go the way from one point to another that takes it the shortest time. Another explanation would be that the interpretation of light as a wave that emanates from each point when it crosses from one medium into another, actually the newly created waves overlap and some have at some points destructive interaction, and only the direction in which the new changed direction of the light ray goes is the one in which they actually have constructive interaction. But as we said, there are many ways to interpret this and many ways to derive it, which we will not be doing here. If you are interested in looking into this yourself, there's plenty of basic physical backgrounds to derive it for you, and you can pick the way or the interpretation of Snell's law that best fits your view of things. But apart from the change of direction, an open question is, if some light may enter a medium, some may reflect, how do we know how much of it is supposed to enter and how much of it should be reflected? As it turns out, this is actually not a number that we can just define for materials in general in the real world, because it depends on how we look at materials. Consider, for instance, the ocean at sundown. When you look at it at a grazing angle, you can't see what's below the surface at all. You will see a bright streak of light from the waterline all the way to the horizon. If you looked at the same water at a time when the sun is at its highest point in the sky, that would not be the case, because more light enters the water, it becomes lit, and the reflection would not be as clear. So the amount of reflection actually depends on the angle theta I of the incident light. For the exact computation of how much of the incoming light should be reflected, we use a principle called Fresnel reflectance. Fresnel reflectance is the result of a physically motivated computation so that we know how much of the light that hits a surface is reflected. The way that we can use Fresnel reflectance differs depending on what kind of material we are looking at. It makes sense to distinguish three different categories of materials to model how they react to the energy in the light that hits them and the resulting models. The first group of materials are dielectrics, which cannot conduct electricity well, such as glass or air, so they let most of the energy just pass through. Conductors, on the other hand, conduct electricity very well, so the energy of light that is not reflected is taken up by the material, for instance by a metal. The third group, semiconductors, is a complex phenomenon, but luckily we don't have many semiconductors exposed to the visible eye, so in rendering we can often ignore them. Today we will be focusing on dielectrics, which either reflect light or let it pass through without absorbing its energy. Here we see a few examples of dielectrics being rendered, with different indices of refraction. We have always replaced one sphere in the scene with the corresponding dielectric material. The change of direction, or perceived warping of light passing through, as well as the amount of light that results in surface reflection, depends on the index of refraction. Notice, for instance, how liquid helium does not focus light all that strongly, and there are almost no specular reflections. On the other hand, diamond with a high index of refraction causes a strong focusing effect, and the reflections, like the light source from above, are pretty significant. We can have a rough categorization of how different physical states map to coefficients of refraction, but there will usually be exceptions, so this is just a rough classification. Now let's check how we can use Fresnel to compute the amount of reflected and refracted light for dielectrics. Fresnel reflectance defines two formulas for the amount of reflected light depending on whether it is parallel polarized or perpendicular polarized. As we mentioned before, in a geometric optics setting, we will ignore the effects of polarization, so we assume that all light is unpolarized. In that case, we get the amount of reflected light from the average of the two squared factors for both types of polarized light. The Fresnel reflectance term Fr already tells us the portion of reflected light. And for a dielectric, we assume that all light that is not reflected enters the material and keeps going. So the amount of reflected light is 1 minus Fr. We now have almost all the building blocks for defining the behavior for light in a dielectric. We know how much light is specularly reflected, and we can handle that with the specular BRDF that we previously derived. We also know how much light enters the object, and we know how to compute the new direction of the light if it is refracted in a dielectric with Snell's law. Now we can try to derive a specular bidirectional transmittance distribution function, or BTDF for short, that we apply to that refracted light, much like we used the BRDF for the reflected light. We start with the basic starting point that we also used for the specular BRDF. The refraction in a dielectric is specular, meaning that all light that enters the medium from a particular direction is also forwarded in a single direction. But in contrast to specular reflection, the angle theta of the refracted ray to the surface normal is not the same as the incident angle. Because the ray is bent, the light goes in a different direction. Remember that the basic unit we use in rendering is radians, which is differential flux per normal projected area per solid angle. If we change the direction of the ray as it passes into a new medium, that directly affects the radiance of the continuing ray. Let's use the definition of the outgoing refracted flux as a function of the incoming light. We can compute the amount of energy that enters the new medium as 1 minus the Fresnel term to equate them. This looks like a pretty complicated setup with no clear way to resolve it, but if we take Snell's law and derive it with respect to theta, we get a helpful term that relates the cosine of the theta times the differential to the index of refraction. And we can substitute this into the equation for ingoing and outgoing light during refraction. The final equation tells us that the radiance that the light carries after refraction is equal to 1 minus the Fresnel term times eta O squared over eta I squared times the incoming radiance. And with that, we have finally acquired all the definitions that we need to define the specular BTDF for dielectrics. Much like last time, since the behavior is specular, we can use the delta function as a basis. We also define a helper function that computes for us the ray that we would get if a light ray is refracted at the interface. This is the refractive equivalent of the mirror direction RV that we used for specular reflection. The total integral of the BTDF times the cosine of theta should integrate to eta O squared over eta I squared times 1 minus Fr. From the specular reflection, we know that for the delta function to achieve this, we must add a compensation term of cosine theta for the formal definition of the BTDF. Notice though that in practice, several of these terms will cancel out in your implementation of the specular BTDF, as they did for the BRDF. If the last step of compensating for the change in directions seems a bit challenging to understand, don't worry, it's fine to think about this for a bit. But as a start, consider the hint that when the rays are bent, the density of the light they carry changes. For a new material with a higher refractive index eta, the energy that is brought in will therefore be compressed into a smaller set of angles. As a consequence, the BTDF does not guarantee the Helmholtz reciprocity. But what it does guarantee is a variation of it that factors in the compression or expansion of light along bent light rays, depending on the refractive indices of the materials involved. That means that, because in our examples we usually follow a view ray and not a light ray, all the steps that we described above can be done in the reverse direction as well. If you follow a view instead of a light ray, just make sure that you pick your refractive indices in the correct order. Eta I should always be for the medium that the ray comes from, and eta T should be for the medium the ray goes to. For the implementation of dielectrics, you might want to consider the hints given here. The first would be that you don't need to complexly factor in the Fresnel terms into your BRDF or BTDF. It's much easier to just draw a random variable and let it decide whether your ray should continue as a refracted or a reflected ray. We have seen this concept before, for instance, to choose a particular light source or for multiple importance sampling, where we make a choice and then later compensate for that choice. With that concept, the changes you need to make are rather small. In the above equations, we always referred to how incident light passes through media. You will be following a view ray, but because you can have a variation of the Helmholtz reciprocity, you can just do the same steps with a view ray as well. In general, you may find it easier to flip the normal of the surface that you hit, if necessary. We currently defined our equations for incident light coming from the same hemisphere as the normal. So in order to reuse the same equations when light that has entered the medium, like glass, exits it again, consider simply flipping the surface normal to compute the newly refracted direction after the light exits. Lastly, while you compute your solutions for theta t from the values you have available, you may end up in a situation where it seems like the sine of theta t, or the mathematical equivalent of it according to geometric and trigonometric equalities, is larger than 1. This would be a good indicator for total internal reflection occurring, in which case you can just cancel the refraction. For details there, we recommend that you take a look at Chapter 8 of the PBR book. This already brings us to the second part, where after we have discussed dielectrics, we now talk about a few effects that become more prominent as soon as you enter them or insert them into your scene in path tracing that you should know of, and that perhaps we can now put in relation to the behaviors we just discussed. The first will be chromatic aberration. When light enters a medium and is passed on, the bending effect is actually dependent on the wavelength of the light. So red, green and blue parts with their different wavelengths on the spectrum actually will be refracted differently. This is exactly the effect you would get if you look through a strong lens, like a magnifying glass, and you seem to see multicolored streaks around the borders of objects. Of course, we could do something like this in path tracing and always pick a certain frequency that we follow randomly. But usually this effect is again ignored due to the diminishing returns on overall image quality, and it only occurring in rare cases. Now that we have the ability to do both specular reflection and refraction, we should also introduce something called the Heckbird notation. This was initially introduced by Paul Heckbird and is now a widely used concept to describe particular paths of light. We already know that some paths may be more challenging than others. If we mix specular materials with diffuse ones in our scene, we saw that this usually leads to a higher variance and sharp isolated details that need many samples to get a decent image quality. Or you may see it when you do the assignments that go along with the lecture. Properties like this can easily be expressed with the Heckbird notation. We use the basic letters L for a light source, D for diffuse surface hit points, S for specular interaction, and E for the end of the ray at the eye. A full path can then be described by a regex combination of these letters. For example, a direct path from light to eye would be denoted LE. Any path from light to eye could be denoted as L, followed by 0 or more of either D or S, and finally an E. You can see how this enables us to isolate paths that have a particular history. But do we have some meaningful examples for this? This brings us to the last point for today, which is caustics. You probably heard that word before, maybe even during the lecture, without having a clear idea of what it actually is. Generally, we use the word caustics to refer to the effects that are generated by curved, specular surfaces. The resulting focused light often has a ring-like shape to it, or an overlapping of rings that give us a localized pattern of bright light and look particularly interesting. For rendering, we can break down the idea of caustics easily with the Hegberg notation. We refer to any path of the form L followed by at least one S and then D and then E as caustics. So a path that starts at the light, hits one or more specular surfaces, and then another diffuse surface before reaching the eye. As you may already have seen in renderings with mirrorspheres and dielectrics, their presence usually causes those bright spots and patterns on the surrounding diffuse surfaces, and it can take quite some time for them to converge to a stable image without any noise. This already brings us to the end of this part 1 on materials. We have a few recommendations for you, mostly resources by Natty Hoffman, who is a great presence in the field of materials and rendering and is always happy to share his extensive knowledge on these subjects. If you want to, feel free to check out his talks and courses. We can highly recommend them. And we hope to see you again for the next part, where in Materials 2, we will be talking about more complex materials, such as the microfacet material model and similar other more complex variants. Thank you for being a part of this, and we also hope to see you next time.